Hi, linear algebra students. So in this video, we're going to prove the Cauchy-Schwarz inequality now that we have the right setup to do it. Okay, so we are in the section that talks about projections. So I will need to recall a little bit about projections before we can actually jump in the proof. And you already have a lot of detail on the board, so let's summarize that. So first of all, what is the Cauchy-Schwarz inequality? It says that the absolute value of the dot product between two vectors is always smaller or equal than the product of their norms, okay? And this is a statement about angles. So let's get started. So first of all, reminder number one, it's this drawing pretty much, okay? So you have two vectors, u and v. So you have to focus on the green and the red vectors that are over here. And regardless what they are, what we saw is that we can always decompose the vector v into a component that is parallel to u, so the projection of v on u, plus a component that is perpendicular to u. Okay? And we saw that their formulas were this and this. Okay, so the projection is the dot product over the norm of u squared times u, and the perp is simply v minus the projection. Okay, so this is how these vectors are constructed. And one thing I also want to mention before we do the full proof, because this is pretty much how you can think about the proof, is looking at the extreme cases, okay? So at best, the vector v will be lined up with u. And if that happens, the equality will actually hold. So I've done the calculation over here. So if v is a scalar multiple of u, then the norm of like the absolute value of u dot v, so you can say like u times ku, then you can pull the k out, then the norm of u times u is like the dot product of u times u is u squared, the norm of u squared, and then you can enter the k inside one of them and say that it turns out to be the norm of v, okay? So this is just letting you know that when the two vectors are lined up, you actually have an equal sign instead of an inequality. And then if the two vectors don't line up, then it will be the general inequality. And if the vectors are perpendicular to each other, then in this case the dot product is 0. So so you get like the worst case in some sense. So how do you prove this Cauchy-Schwarz inequality? Well, the only thing you need to do is to state that that perpendicular vector right here, whatever it is, it has to be greater than 0. So let's actually write this down. Whatever perp u of v is, its norm must be greater than 0. Okay, and now that we have this laid out, let's erase the extreme cases because I will use that space to do the proof. But I like these two formulas, so I will leave them on the board. Okay. All right, so the idea is to write that the norm of perp u v, okay, and we will square it out of convenience, is greater or equal to 0. Now, remember that a property of the dot product is that the dot product of a vector with itself is the norm squared. So that's basically what we're using. So what we want to do is we want to do the dot product of perp u v with itself. Okay, and now let's actually use this formula. So we will get here v minus projection uv dot v minus projection uv. Okay, and remember that the dot product is a very nice operation. It has a lot of properties. For example, you know that it's both left and right distributive. And you also know that it's commutative. In other words, you can pretty much expand it like a polynomial. I did this calculation before, so I will jump some of the steps. I will skip some of the steps, sorry about that. So you get like v dot v, which is the norm of v squared. Then you're having twice, so minus twice v times the projection of u dot v. And then finally, you have plus the norm of the projection of u dot v squared, okay? And you get that this is greater or equal to 0, okay? Now, the norm of v squared, there's nothing we can do about it, but we can certainly simplify both of these things. So let's call this step number 1. And then I will focus on this guy, let's say. And this will be step number 2, okay? Now what we do is, okay, we have our 2v dot. We will use the formula that we have right here, okay, where you have, this is a number, u dot v over u squared. Okay, so like this. And then multiplied by the vector u. Okay? And, okay, so as you can see, what's going to happen is all the numbers go out. So we get like this. Okay, so u dot v over u squared. And then this vector v is being dotted with u. Okay? And as you can see, this is the same calculation of u dot v, the one that is right here. So let's finally write the fully simplified form. We get twice u dot v squared divided by u squared. Okay, so this is number 2. Number 3. So now we're going to focus on this guy. And we're going to compute it. So projection of v on u, all of it squared. So obviously we're dot producting this with itself. Okay, so funny to say. Or we can actually go faster. We can go like directly. Okay, so that's going to be the norm, like over the norm of u squared times u. Okay, and that's going to be squared. And that's going to give us something really simple when you think about it, because so this constant will come out being squared. Okay, so we will get here u dot v over u squared, and all of this will be squared, and then we will take the norm of this vector u right here, that we will square. Now be careful, this will be u to the power of 4, so overall what do you get? You simply get u dot v squared over u squared. Okay, so you just simplify this with this, but be careful, this is to the power of 4, and you get that. So going back to step 1, where we replace this thing. So let's call this step number 4, pretty much. Okay. So what did we get? We get that the norm of v squared minus this, so 2 u dot v squared over u squared. Okay. Then plus this thing, so plus this, so u dot v squared over u squared is greater or equal to 0. So then we will start moving things around, okay? And actually, before we do this, let's combine this with this, because as you can see, it's the exact same thing. So we finally get that v squared minus u dot v squared over u squared is greater or equal to 0. And as you can see, we're almost done. So let's erase this. All right. Now the only thing we need to do is to push things around. So this goes on the other side. We have v squared is, or actually, let's, can we skip a little bit of steps? We can say that v squared times the norm of u squared is greater or equal than u dot v squared. And then as you take the square root of, so square rooting both sides, square rooting both sides, like I will put this in quotation. This is obviously kind of an invention. Square rooting both sides will give the norm of v times the norm of u, which is greater or equal. And now, okay, so this side is always positive, so we don't need to worry about it, right? But this side, the u dot v, that could be negative. Remember when u is pointing somehow the opposite direction of v. So you have to, whenever you're taking the square root, you have to put the absolute value. So there it is. Like, keep in mind that when you take square roots, you would normally put plus or minus. But again, that doesn't apply because, well, in some sense, it applies to both sides. Like if you put like a minus here, it will mean that you're not putting the absolute value. So there it is. I hope this is helpful. See you either in class or in the next video.